All right. I think we can start now.
So, greetings and a warm welcome to all the esteemed dignitaries and participants joining us today. I am Trishna from Clarinet and I'll be your session assistant for this evening to ensure that we have a smooth and enriching experience together. Clarinet is proud to be India's most trusted digital platform dedicated exclusively to serving the medical community. And I would like to extend my heartfelt wishes and welcome to all the participants. And we are truly honored to be the digital partner for this special event hosted by the Jaipur Society of Anesthesiologists. Today's session focuses on PG Assembly Program Anesthesia Workstation. And without any further delay, I am pleased to welcome Dr. Chitra Singh ma'am to officially begin today's session, and I'll be displaying her CV. Dr. Chitra Singh is currently serving as the Professor of Anesthesia at Trauma Center, SMS Medical College, and also serves as the Joint Director at SOTO. She has attended SMS Medical College and Hospital, and her areas of interest include trauma and transplant anesthesia. She has several special achievements, such as faculty at Skill Lab and Oro Outreach, faculty at various national conferences, including the MAMC, AIMS Delhi, AIMS Jodhpur, and she has been awarded the Certificate of Excellence by Principal, Superintendent, Chief Minister, Health Minister, and non-governmental organizations. So, with this, I hand over the session to Dr. Chitra Singh, ma'am.
Good evening. I'm delighted to welcome respected persons, speaker, the organizers, and dear PG students on the third PG Assembly webinar on Anesthesia Workstation hosted by JSA in collaboration with Department of Anesthesia, SMS Medical College, and Jaipur Anesthesiologist Academic Foundation. I hope the lecture advanced the integrated technologies, precise checklist, and advancement from the traditional boundaries. I hereby welcome the chairpersons, Dr. Avnish Bhardwaj sir, Dr. Avnish Bhardwaj sir, he is an eminent Dr. Avnish Bhardwaj sir is Emeritus Professor of Anesthesiology at Mahatma Gandhi Medical College, Jaipur. He is a teacher of teachers. His interest is teaching and mentoring. Sir has various achievements as Sir has served as a National Council, Governing Council member from 1997 to 2000. He had been a former editorial board member in Indian Journal of Anesthesiology, Internet Journal of Anesthesiology, Indian Journal of Clinical Anesthesia, and Current Medical Trends. Sir had been an organizing secretary of ISA National Conference Jaipur held in 1994. Sir had been an honorary secretary RSA, JSA, ISSP, and JMA. Sir has illustrious alumni of SMS Medical College and has lifetime achievement awards from JSA and JMA. Sir Avnish Bhardwaj sir is a global expert and has a profound knowledge. His integrated wisdom has shaped in precise decision making with predictive outcomes. His contribution is subtle yet evident in reshaping the branch. I welcome Tarun Lal sir. Dr. Tarun Lal sir is a senior professor in Department of Neuroanesthesia, SS Medical College, Jaipur. His areas of interest have an automatic CPR machine. He's working on AI in medicine since last 26 years. Sir had been a principal and controller as SJP Medical College. In addition, principal at RUHS Jaipur. He had charge in Institute of Public Health RUHS, holding 11 operation theatres at RUHS Jaipur. Sir had been in charge of 305-bed ICU of RUHS Jaipur, and as well as in charge of generation plans He had been in charge of skill lab of BLS and has served as additional nodal officer in charge at Trauma Center SMS Jaipur. Sir has got a practical and tailored approach to sharpen these clinical skills. I would request Dr. Tarun Lal sir to introduce the speaker.
Thank you very much, Dr. Chitra. Good evening, all of you. Good evening, Dr. Avnish Bhardwaj, sir. Good evening, Dr. Aditya Sapra, sir. Dr. Chitra, ma'am. Dr. Akhil Agarwal, sir. Dear residents and dear colleagues. Today we are here to discuss the most important topic of our lives, and that is the central hub around which all our lives matter, the central hub where technology and clinical judgment come together for the safety of the patient. And we are here to discuss the anesthesia workstation. We're here to discuss the anesthesia workstation, the most important, the heart of the operating theater, the heart of everything here. So I would request Dr. Aditya Sapra also to give us a few words to tell us more about the anesthesia workstation. And I just want to know just how many residents are there right now. Do we have residents from SMS Hospital? Because we've worked, Dr. Avnish sir would tell us, Dr. Chitra ma'am, Dr. Aditya Sapra, we've worked on hundreds of anesthesia workstations, from the major Boyle's machine to the highly technological savvy Drager machines. And we've also worked on the Schimmelbusch mask, where if you were to see this is the gauze piece, and if I can say this is something akin to the Schimmelbusch mask, for historical interest, we could the open drop method, We have worked on this also, and we worked on the Drager Atlan highly sophisticated machines. So we've come a long way, hundreds and thousands of workstations that we worked on, But there are certain common things, which would be in all the workstations. So do we have some residents here? Do we know any residents from SMS Hospital?
Good
Are
evening,
there any
everyone.
residents? Hello?
Good evening, everyone. Sir, I am Dr. Vinu from SMS Medical College.
Oh, you're from SMS Hospital. What's your name?
Sir, Dr. Vinu.
Dr. Vinu. So which anesthesia workstation are you working on?
Sir, I'm working on Resin Atlan A350 workstation.
Drager Atlan A350, right?
Yes,
The
sir.
one which has the electronic flow meters?
Yes, sir.
I see. Okay. So you're from SMS and you're working on this Drager. Why do we call it a workstation? And what's so important about this workstation? Why it was just a machine first, no? We started calling it a workstation. Probably the workstation, why do we call it a workstation now?
Because it is integrated multiple functions into one system, like
Yeah.
gas delivery,
Very true,
vaporizer,
very true. Yeah.
monitoring.
So now it integrates hundreds of things, the processors, the machines, there's so many things. The digital AI is there. So much of this is there, which were not there in an anesthesia machine. So it integrates so many things. And that is why it's called a workstation. Yeah. Are there any more? What would be the single most important feature in your machine, if you could tell me?
Sir, oxygen analyzer.
Oxygen, oxygen alarms, oxygen analyzer. Yeah, very good. Most important, single feature, be it Penlon, be it Drager, be it any. These would be the common features, of this.
Yes.
And are there any more resident doctors from SMS, from Mahatma Gandhi, from
Good
Fortis?
evening, sir. Dr. Mohan, SMS Medical College.
What's your name?
Dr. Mohan Prakash, sir.
Dr. Mohan. Dr. Mohan, which anesthesia workstation are you working on?
Sir, Penlon, sir.
Penlon.
360 Advanced.
Penlon 360 Advanced. I see.
320.
Okay, so this has the flow meters, right? This
Yes,
has the flow meters, right?
Yes, sir.
It doesn't have the electronic ones like
No, sir.
Vino was working on, right? This has Penlon, right?
Yes.
Very good. So which would be in mechanical ventilation between Penlon and Drager, like the oxygen flush, right?
Yes, sir.
Oxygen flush, if we press it in a mechanical ventilation, will Penlon harm the patient, causing pneumothorax or barotrauma?
Yes, sir, definitely, because it has a high pressure oxygen, 35 to
Oxygen flush
75
may or may
to
not cause, oxygen flush with, if we push 35 liters in a patient with
Yes.
doing
That, yes,
mechanical
sir.
ventilation during inspiration, maybe. But that may not be there in dredger. So that's kind of one advantage. Anyway, so I'll hand over the baton now to Dr. Aditya Sapra, sir. Dr. Aditya Sapra, sir, is a highly accomplished anesthetist. He is from Air Force Hospital, Kanpur, and he holds very high accomplishments, Chief of Army Staff Commendation. That's a very important thing. Chief of Air Staff Commendation, another very important. I belong to a family of Army doctors, so I would know the significance of this. He has had a gold medal for standing first in his MD exam. Another big achievement there. He's head of anesthesiology and critical care, AFMC. He was their commanding officer. So he's held a lot of commanding posts there, commanding officer, Air Force, Hospital, Jaisalmer, then UN mission, he was there. A lot of accomplishments, sir. I will hand over the baton to you. You tell us more about the anesthesia workstation. Thank you. Dr. Sapra, sir, would you be there?
Miss Trishna, can we have the video, please?
Yes, sir, I'm sharing.
Good evening, everyone. At the outset, I would like to thank the Jaipur Society of Anesthesiologists for giving me a chance to speak on this wonderful topic during their PG assembly. It is a topic that is close to my heart, and I believe that if all of us have to provide safe anesthesia, we should be totally familiar with how the anesthesia workstation works. So in today's talk, I'll start with the history. We all know that after the successful demonstration of ether anesthesia by W.T.G. Morton in 1846, many innovations, many kinds of inhalers had come up. But the credit for the first successful nitrous oxide oxygen apparatus goes to Gothmi, who published his first textbook of anesthesia in 1914, in which he had described this oxygen nitrous oxide apparatus. Now, James T. Gothmi was a captain in the American Army Medical Corps, and for the First World War duties, he was posted to France in 1914, where he met another captain from the Royal Army Medical Corps, that is H.E.G. Boyle, and that is where Boyle first saw Gothmi's apparatus. When he came back to England, he modified this apparatus. He made sure that some of the shortcomings, like the leaks, the joints, they were improved. He added a few innovations on his own. And then with the British Oxygen Company, he brought out the first commercial anesthesia apparatus. And that is why till today, we call all our anesthesia workstations the Boyle's machine. After that, a lot of improvements kept on being added by various innovators. The initial machine, surprisingly, did not have any pressure regulators. It was just one cylinder, and the anesthetist was expected to adjust the flow so as to provide the right amount of oxygen and nitrous oxide without causing any harm to the patient. The pressure regulators became a standard fitment along with bobbin flow meters around early 1930s. And at the same time, a lot of work was being done on using low flow gases. So the first step towards that was probably Ralph Waters' to and fro canister. He showed that if carbon dioxide could be absorbed from the exhaled gases, then the exhaled gases could be reused. Then the circle absorber, which you can say was the forerunner of what we use today, was introduced by Brian Sword in 1928. And now successful administration of low flow anesthesia required precise delivery of gases at low flow, for which these bobbin flow meters were not good. So we have in 1937 Richard Salt, who is credited with introducing the rotameters onto the anesthesia machine. Now, rotameter industrially, it had been invented in Germany. It was in use since early 1900s, but Richard Salt developed it for use in the anesthesia machine. And further innovation was by Thorpe, who gave us the precise vertical tapered tube so that we could have exact flows, exact measurement of flows of our gases. Woodbridge is credited with introducing the pin index safety system, which was widely adopted by the British Oxygen Company in their cylinders and machines, and accompanied with Bodoc seal. This is how the initial machines were being marketed by 1950, 1960. So after that, a lot of safety features, a lot of electronics, a lot of computers have been added to the anesthesia machines, but the essential structure, the plumbing, as we may call it, remains more or less the same. Now let us just go to the description of the modern anesthesia machine. So whenever we talk of the anesthesia machine, we always talk of the anesthesia, the high pressure system, the low pressure system, and the intermediate pressure system. So for an anesthetist, it is most important to know what are these pressures when we are talking, and to be able to convert these pressures quickly and without any mistakes. So when we talk of high pressure system, so for that, first of all, we should be sure what are the various units of pressure and how to convert from one unit to the other. So 1 atmosphere, we say, is equal to 1 bar. It is equal to 1000 millibar, or we may say 760 millimeter of mercury or 760 torr. And this is also equal to 1030 centimeter of water, 14.6 psi or 100 kPa. Now you will understand how important this is when you just open DOSH and see that this is your table 1.1. So before you read anything about equipment, this is the first thing that they want you to know. And this is the screenshot from table 1.1 of DOSH. And why is it important? Now, this is the machine that I'm going to describe today, the Allied, from the Allied company. And you see in this one machine, these are the various scales that have been used. On the pressure gauges, we see 100 kPa is used. Where they have a outlet for oxygen, they have used 4 bar. And on the ventilator, it again comes back to 275 to 840 kPa. Now, if you are an anesthetist and you only remember in PSI and you know that your pipeline is giving 40 to 60 PSI, when you come across this machine suddenly in the morning, you will have problems. So how do I do it? Well, I learned it from the Air Force engineers. They always think of pressures in terms of bar, that is in terms of atmospheric pressure. And I also felt that if we treat pressures in terms of bars, it is very easy to convert from one unit to the other. So 100 kPa we know is 1 bar, 150 kPa is 150 into 100 kPa, you can see it marked here. That is your full oxygen cylinder. So 150 into 100 kPa is your full oxygen cylinder, which means about 150 bar. 4 bar is your pipeline supply. And now if I have to just see how much is this 275 to 840, I know that it is about 2.75 to 8.4 bar. And I know that 15 PSI is equal to 1 bar. I can easily convert and see that 15 threes are about, this might be around 45 PSI to 60 PSI or 120 PSI, which is the ventilator's running pressure, the driving gas pressure that is required to run the pressure. So that easy convertibility, we all must be comfortable converting from one unit to the other. Then once you know what is the actual pressure, then we come to the distinction between the high pressure, low pressure, and intermediate pressure. So the high pressure is what you have in gas cylinders. For a full oxygen cylinder, it is about 150 bar, or as you all know, about 2000 psi. For a nitrous oxide cylinder, it is about 740 psi. So starting from the cylinder, then we have an oxygen regulator. So till the oxygen regulator, pressure regulator, it is high pressure. The output of the regulator is intermediate pressure. So the output of the regulator, starting from the output of the regulator till just before the flow valve, that is your intermediate pressure system. And beyond the flow control knob, it is all low pressure system. So this particular picture that you see is from Dorsch, and we also have the same thing in Miller's, slightly more colorful, but essentially it says the same things. The cylinder is your high pressure system. Beyond that, till your flow control knobs is the intermediate, and beyond the flow control knobs is your low pressure system. So that is how, because this will be asked in exam, so this you should be able to show on the machine. Now on the machine, when we see, so as I told you, we have this Allied Jupiter 500 machine. And what I have done is we have just opened this tray, and then this is how you will see the machine. And these are the various parts. And now we will just cover these parts one by one. Another part of the high pressure system is the Bourdon gauge. The Bourdon gauge is what actually shows you the cylinder pressure. So the cylinder is connected, the pressure of the cylinder is transmitted through this connector here. And then the Bourdon pressure gauge shows you the actual pressure inside the cylinder. So it is also a part of the high pressure system. And how does the Bourdon gauge work? Well, if you just turn it around, you see that there is a curved copper tube, and as you can see, this is transmitting the cylinder pressure. So as I turn on the cylinder pressure is transmitted to this tube, and this tube tends to straighten out. Now if we see all these nomenclature on this that you see, the A, B, C, D are the fixed parts of the Bourdon gauge when seen from behind, and all these numbers 1 to 9 are all the moving part. So you can see that as the pressure has come from somewhere here, this end, gone through that curved tube, come here, it has caused this tube to move. And you can see that through this 4, 5, 6, 7, 8, and on the other side of this machine is the needle, this needle. So all this mechanism that you see here, it is connected to this needle, and as this moves, the needle moves and it shows you the correct pressure. So that is how the Bourdon gauge works. The next thing, the next structure in the high pressure system. So what we have seen is that this is the high pressure system. You can see here that somewhere here would be the cylinders. So of course, that is the high pressure system connected through the pin index system on the yoke assembly. This is your pressure regulator, and this copper tubing that you see here, the copper tubing that you see here, this is what is taking the pressure to the Bourdon gauge. So I have covered the Bourdon gauge. Now let us see how a pressure regulator works. Then we will come to the other connections in the high pressure system. Now the pressure gauge, the pressure regulator works on the simple principle that force upon area is equal to pressure. Or as you all know, the definition of pressure is force per unit area. Now the pressure varies as per the area of the diaphragm to which it is exposed. Now, if we look at this fulcrum, so on both the sides, when there is no gas flow, on both sides of this fulcrum, the forces are balanced. So we know that pressure is equal to force upon area, or we can say that force is equal to pressure into area. Now, if we say that let the cylinder pressure be PC, what you see here, and the area be A1. So we can say that PC into A1 will be equal to whatever pressure is the output of the regulator into A2. So a very simple calculation would be that the output pressure of the regulator will be the cylinder pressure into the ratio of A1 is to A2. And if I know, this is what the company has to design. If I know the ratio between A1 and A2, I can decide the output pressure. But as you can also make out, there is a problem with this. that as the pressure in the as the pressure in the cylinder keeps on falling, the output pressure will also keep on falling. So the anesthetist will have to be very vigilant. And as the cylinder pressure keeps on falling, you will just have to keep on increasing the flow, turning the flow control knob, adjusting the flow, and obviously quite a cumbersome deal. So what did the engineers do to help us solve this problem? So this is the thing in action. Sorry, I'll just come to that part also. So this is the pressure regulator in action. So what has happened is I have turned on the stopcock here, which leads to initial flow of gas. This falls. The pressure here falls because the gas has started flowing. And as the pressure falls, you can see that this outlet opens, allowing a continuous flow of gases till the stopcock is turned off again. So that is how it will work. But the problem is that as the cylinder pressure keeps on falling, the output pressure will also keep on falling, and therefore I will have to be vigilant. I will have to keep on adjusting the flows to match the cylinder output. So what did the engineers come up with? They came out with the idea of an adjusting spring. So now in this design, what you see has been added is this spring S1, which is a very large force as compared to the pressure or the forces that we were talking about, so that all these other pressures, the changes in the other pressures become inconsequential. So suppose now let us examine that. Now I will just show you the equation first. Then now what are the forces that are trying to open the cylinder will be your pressure in the cylinder into A1. And if you see this S1 is also, because of its downward action, it is also trying to open the cylinder. And what are the forces that are trying to keep the cylinder closed is equal to, it will be your output pressure into A2. And although they have not labeled this, and this is again from Dorsch, if they have not labeled it, but we can call this S2, as you can see in subsequent diagrams in Dorsch. So if you want to take it S2, then this will be S2. So now if we work out the thing for PC into A1 plus S1 minus S2 and the whole thing upon A2. So this will be your output. Now, what I was saying is that suppose this S1 minus S2 is a very large number. Then what happens is that this change becomes inconsequential. Whatever is the PC, suppose it was 2000, now it has become 200. It is earlier equation, it would have resulted in the output pressure being 1/10. But now if S1 minus S2 is a large figure, arbitrarily, let us say it is 20,000. So whether you add 2,000 to 20,000 or you add only 200 to 20,000, the output regulator pressure remains the same or only a marginal difference, not that tenfold difference which we were experiencing otherwise. So this is how the two, so one is the adjusting spring S1 and the other is the spring which you can say is kind of a counter pressure so that to balance this spring S1. Now this equation I have copied from Dorsch. And this is just to warn you that if you go back and read from Dorsch, there is one error in this. So till here, the equation is correctly solved, and you can all see that Fs1 is equal to Pc into A1 plus. So what they have done is they have not included S2, and this part of the equation they have mentioned correctly. Now the error is here. This should have been equal to. If it is equal to, then you can see that this is exactly what I have also written, PC by A2, PC into A1 upon A2. That is this part is what is written here. And PR into FS1 by A2 is the second part. Oh, PR, this would be equal to, and FS1 by A2 is the other part, S1 by A2. This is what it would have been. So that is the mistake. So you can just go back and correct it in your book and then read it. It will make sense to you. So this is how they have prevented the minute to minute change as gas flows out. Now there is one more problem. As you saw in this first example, the two examples that I have given to you now, till now, the cylinder pressure is trying to open the valve. So inherently, it is an unsafe method because there will always be a problem, or there will always be a positive pressure inside the cylinder. And if inadvertently I have not taken care with the knob, then this pressure will open the cylinder. So will open and allow flows. So what have they done now as a safety precaution? Now in this second, which is the indirect arrangement, in the indirect arrangement, what they have done is they have started, they have converted it so that the cylinder pressure, as you can see here, now closes the flow. It stops the flow. And to open the flow, now suppose I open the flow, then there is a fall, this will go here. Only then this will move up and start the flows. This, when I say this, I mean this white thing. And this will move up only when the balance tilts this side, this will go there, and then the flows will start. So by default now, the cylinder pressure is trying to close the flows, the regulator flows. So this is what is incorporated in the modern anesthesia machine, an indirect type of a pressure regulator. So now we come back to this tray and we will just see what are the various parts. So as I told you, the high pressure system, the yoke assembly, here would be the pin index system with the Bodox seal. Then we come to the pressure regulator. And from the pressure regulator, you can see this metal tubing taking us to the pressure gauge, which is also the high pressure system. The output of the regulator, this is the output of the regulator. So the output of the regulator, because now it is intermediate, so you can see that we can use plastic tubing. So the output has come. This is the output of the second regulator. The two meet and they go further. So the first outlet after this is this. So what could this be? This is oxygen flush. So as you all know, oxygen flush is connected directly to the intermediate pressure system. Yes. And from the oxygen flush, that is when I will press it here, where does this outlet go? Sorry. So one of the connections is from the oxygen flush is directly going to your common gas outlet. This is what I wanted to show you. So when I press the oxygen flush, you will see that the output of the oxygen flush is going directly to the circuit, to the common gas outlet, which means that when you press the oxygen flush, the patient gets oxygen at high flows at 40 to 60 psi pressure, which is enough to cause barotrauma. So that is why we never use it when the patient is connected. So now let us trace the oxygen further beyond oxygen flush. Now, just as we see, there are three things that attract attention. One is this large aluminum thing, which has battery written. The other is probably this large thing. And the third is this black plastic thing. So let us just see what they are. The first thing that you see where battery is written is your hypoxia alarm. So it is that inaccessible, unmutable hypoxia alarm, which is exposed to 40 to 60 psi of gas pressure. And the moment the gas pressure falls below 40 psi, this oxygen alarm is triggered, and then the anesthetist cannot mute it because it is hidden under the tray. And you see there is no mute button also on it. That is the first thing. Next, we come to this aluminum cube, which you can see is clamped to the machine. So let us see, we have just removed the clamp here, turned the thing around. And what is this? So you see that it has connections from both oxygen, the white one, and nitrous oxide. So what could this be? And this probably indicates that it is some kind of a pressure sensing device. So this is your master, probably this is a master slave device where the nitrous flow is controlled by the flow or the pressure of the oxygen pipeline or in the oxygen line. So the oxygen line, if it is exerting enough pressure, only then it will allow the flow of nitrous oxide. So this is a master slave assembly, again a hypoxia prevention device. Third thing we said is this black plastic thing. So again, we open it and we turn it around, and you see that it has an inlet pressure. It has a range from 0 to 100 psi. So this is a second stage oxygen regulator, oxygen pressure regulator. So the first stage, this was the first stage pressure regulator, which has brought down the pressure to maybe 40 to 60 psi. And beyond that, then it is further reduced so that when the by the time the oxygen reaches the low flow system, the pressure has already come down sufficiently. So this regulator will reduce the pressure to around 10 to 20 psi. So these are the various connections that you have just seen on inside the thing. Then after so we saw that it had reached the oxygen flush. Then beyond the flush, we saw it reach the hypoxia alarm. Then it has gone and come back for the master slave assembly. Beyond that, it has gone back again and it has gone to the flow meter somewhere. On the other side, we have similarly the nitrous oxide. The nitrous oxide, these metals you can understand is probably going to the gauge. The plastic tubing is the output. The two outputs are connected. Again, coming to the master slave to decide whether the flow can be permitted or not, and only then going to the flow meters. So this is how the anesthesia machine plumbing looks like from the inside. And now this I have just once again to show you and to show how it corresponds to what we see on the outside. Now, when we are looking from the outside, where you have the common gas outlet, this is your where we also have the closed circuit or open circuit selector switch. So the common gas outlet is here. That is just your distribution. And from here, the gases have gone to either the common gas outlet or it has gone to the closed circuit. So this black tubing, you must remember, because this black tubing we will cover it once again when we come to the closed circuit. So here you have the closed versus open circuit selector switch, and this, as we covered, is your oxygen flush and then the common gas outlet. So from the outside, it will look like this. So now, if we just go back to what we saw in the book diagrams, till somewhere here is till somewhere here minus the output. So this part is your high pressure. Then with the outputs, everything else that you see on the tray is all intermediate pressure system. And then beyond the intermediate pressure system, what we see on the outside is your low pressure system. So in the low pressure system, what is important is your flow control knob, the flow tubes. And as I covered in the history part also, this tube, this vertical tapering tube, is what is known as the Thorpe's tube. And if we look at it in cross section, you can see that around the bobbin here is the annular space. So that annular space is the diameter of the size of the annular space is what determines how much flow is going. And these tubes are precisely calibrated for a gas. So in the olden machines, sometimes there would be a temptation that I have lost one bobbin, so can I use the bobbin from the adjacent tube for oxygen? No, the bobbin, the tube, everything is calibrated for the particular gas that it is to be used for, and therefore these are not interchangeable. And it should be used only from that precise manufacturer, because it is just meant for that particular tube only. And how to read the bobbin also, this is important. So in a non-rotating float or in a plumb bob float, we read from the top. If it is a ball, we read from the middle where it touches the wall. On a skirted float, again, we read from the top of the float. Now, again, one question that is commonly asked, and what is again important for all of us from the safety point of view, is how is the flow meters arranged on the anesthesia machine. So this is a diagram from Miller's again, which shows 3 or 4 different types of arrangements of the flow meters. And what we must always remember is that oxygen should always be the last gas that is added to the circuit. So oxygen should be downstream. Why is it important? Now let's assume that oxygen is upstream, either at number 1 or number 2 position. And suppose there is a leak. Then whenever there is a chance that only oxygen is leaking, then there is a chance that the patient will get a hypoxic mixture. Whereas if oxygen is the last gas that is added, so now if there is any leak beyond the point where oxygen is added, then the entire mixture will leak. Only oxygen will not leak. So what I mean to say is, now suppose we have this arrangement A, where oxygen, suppose I'm giving it 1 liter, nitrous I'm giving it 2 liters. But from here, 500 ml oxygen is leaking out. So by the time the mixture is formed, the patient gets only 0.5, but he has got 2 liters of nitrous. So I wanted the ratio 1:2. Patient is getting the ratio 1:4. But from here, but in this arrangement, in the last arrangement, suppose same, I have used the same. Now, if there is a 0.5 liter leak also, then this 0.5 liter leak, both nitrous and oxygen are being lost. So my patient will not get a hypoxic mixture. So the thing to remember is that oxygen should always be downstream of all other gases. Another safety feature in the anesthesia machine these days is your oxygen proportioning devices, and we have 2 common types of proportioning devices: the SORC, that is the sensitive oxygen ratio controller, and the Link 25. So SORC, this is usually seen in dragger machines. And here you can see the blue line is nitrous, the green line is oxygen. And because of the oxygen pressure, this piston is pushed that side, which allows the proportional amount of nitrous oxide to flow. And as the oxygen pressure falls, the nitrous pressure also falls. So that is a sensitive oxygen ratio controller used in dragger devices. The more mechanical type of device which we see in most of our machines these days is your Link 25. So Link 25 works on the principle of the differential cogs in oxygen and nitrous assemblies. So in the nitrous oxide side, we have 15 teeth, and on the oxygen side, we have 29 teeth. So which means that each turn of the oxygen flow control knob will result in two turns of the nitrous oxide knob. So that means that the ratio that is delivered is 1:2, or 33% of oxygen. But then it is called Link 25, which means that it will give at least 25% oxygen. So with this arrangement, you can see that the ratio that is given is 1:2, or 33% oxygen. The further reduction in oxygen occurs at the level of the flow control valve. So as you can see in this diagram, the shape of the spindle in the 2 flow control valves is slightly different. Oxygen is the sharper one, and this is the steep taper, which results in more nitrous oxide flowing at the same level of valve opening. So what we had got here was 1:2. By the time it leaves the flow control valve, it becomes 1:3, because now more nitrous oxide can pass through the flow control valve, and therefore the output is at least 25% of oxygen, or that is why it is called a Link 25 system. Now you remember that black tube I talked about. I said that we will come to it when we come to the circle system. So we'll just see what a circle system is supposed to be like. Then we will come back to our machine and see how to identify the various parts on the machine. So the design of the circle system is simple. We have the fresh gas inlet. As the gases come in, the first thing that we encounter is your inspiratory unidirectional valve. Beyond that, we have the humidifier, the oxygen sensor, yes, the oxygen, the gas sampling line, and finally the patient Y-piece. Then we have the expiratory limb. In the expiratory limb, again, we have the pressure sensor, the PEEP valve. Okay, PEEP valve now, it can have three different locations. And we will come to it just now. But PEEP valve here in this diagram, they have shown upstream of the expiratory unidirectional valve, but it can be located either before or after the expiratory valve. So we will just cover it. Then on the expiratory side, so we had the airway pressure sensor, we have the PEEP valve, then we have the expiratory unidirectional valve, and finally you have your selector, that is your bag ventilator selector switch. Then on one side of the selector switch is your bag, and finally your ventilator. Further gases go to your carbon dioxide absorber and then again mix with your fresh gas flows. That is how the circle system is designed. Now, if we just compare it to what we saw on the machine. So I told you that black tube, this is your black tube, and you can see that it has come to this place where fresh gas inlet is written. Beyond that, so this was the diagram, and you can see that this is your fresh gas inlet. Beyond that, we had the inspiratory valve. So here we have the inspiratory valve, and this is where we will connect the circuit. Somewhere here will be your Y-piece and then expiratory limb. So exactly as it is there in this diagram, then we have the expiratory limb and the expiratory valve. So this is your expiratory unidirectional valve. Beyond which we have the selector switch. So in this machine, the selector switch is on this side. Beyond the selector switch, we will have the bag. You can see that green thing hanging there is the bag. And on the other side is the ventilator. So this is the connection for the ventilator. So exactly as it is given in the book, we have it in our machine. And this carbon dioxide absorber is what would be under this. So that under this console, you have the CO2 absorber. So now how do gases flow? Let us just see. So now let us just see how this system behaves during spontaneous breathing. Now what you have to remember is that in any circuit, whether it be your circle system or it be your Bain circuit or A, B, C, whichever circuit you are using, in spontaneous, the APL valve opens during the phase in which the pressure is higher. So in spontaneous breathing, you know that it is negative pressure inspiration and the pressure rises slightly during exhalation. Whereas in controlled breathing, whether it be manual breathing or whether it be ventilator breathing, the pressure is higher in the inspiratory phase, positive pressure ventilation. So that is why in manual breathing or controlled breathing with ventilator, the APL valve will open during inspiration. So now let us just see how this system behaves during spontaneous breathing. It is actually quite intuitive. If you see, the fresh gas flow is shown with these dark arrows. The light gray arrows show the exhaled gas. During inspiration, the APL valve remains closed, and whatever gases have collected in the system, they will just flow towards the patient because of a negative pressure here. Then in the exhalation part, these gases flow out. Pressure is higher, APL valve opens, some of the excess gases move out, and remaining are collected in the bag. Next breath, these, as the patient creates a negative pressure here, these gases move out. If it is an exhaled gas, it then passes through your CO2 absorber. CO2 is absorbed. What is left is clean gas, mixes with the fresh gas, and then the patient has now got gas that is free of carbon dioxide. And that is how the cycle continues. When we come to manual ventilation, in manual ventilation, I told you that the APL valve will open during inspiration. So as I give the breath, I press the bag, the APL valve is open, the gases go out, the other gases will now go through the canister, mix with fresh gas flow, and go to the patient. During exhalation, because now you see this APL valve is closed, so everything just comes and collects in the bag, and in the next breath, again, these gases will move out and start flowing towards the patient. That is how it happens during controlled ventilation. Now, I have written here low flows. If the flows were very high, that is why if it is low flow, it reaches only till here. If the flows are very high, then some amount of fresh gas flow, because you see that it is a valveless system. So some amount of gases will reach the bag, and so the bag will contain some amount of fresh gas also. At low flows, the bag will contain mainly exhaled gases. What happens during mechanical ventilation? Now, mechanical ventilation, you'll see that the bag selector switch, this is now towards the ventilator. So the bag is now out. The bag will be out, and the gases, the same in a similar manner. What was happening earlier with the bag, now the same kind of flows will start happening with the ventilator. So the gases will flow from here to the ventilator during exhalation, and during inhalation, they will take this route and what we have shown here in the diagram on the left, and they will reach the patient. So this is how the gases flow during manual and controlled ventilation through a circle system. Now, the question that many of you sometimes ask is that why is the ventilator kept upstream of the CO2 canister? Can't the ventilator be somewhere here? Then the ventilator only has to push this much. Now the ventilator has to push through this much extra resistance. So yes, some machines do come with a ventilator which is placed after the CO2 canister. But just look at what will happen to the flows when the ventilator is at this location. Now, can the gases go in this direction? No, because there is a expiratory unidirectional valve. But if I place the ventilator in this location, then what will happen? Now the gases can go in this direction also, and the gases can go in this direction also. Therefore, then, if I have to place the ventilator here, I will have to put a check valve so that the gases don't go back into the CO2 absorber. So that is an engineering complexity that is added without giving you much additional benefits, yet it is present in some machines. So yes, you can keep it there, but then you have to remember this extra point. An essential component of the circle system is the CO2 absorber. And CO2 absorber, there are certain things which you must know. Which are the compounds used? Commonly used is soda lime. So what is the composition of soda lime? You should know. What are the equations you should know? So for this, again, we fall back to Miller only because Miller has given this quite well. So this is the net reaction that takes place. And there are three steps in this reaction. The first step is CO2 plus water becoming H2CO3. Then H2CO3 reacts with the strong base. So there are two strong bases, sodium hydroxide or potassium hydroxide. So this is a fast reaction. H2CO3, a weak acid, reacting with a strong alkali, giving you Na2CO3 or K2CO3. And you can see that this is a reaction which generates water, and this is a reaction which generates heat. Then this sodium carbonate or potassium carbonate, which is formed in step 2. Now, because it can react with CaOH2, that is calcium hydroxide, and this finally forms calcium carbonate with 2 sodium hydroxide. And if you remember from your 12th standard days, what is the definition of a catalyst? A catalyst is something that has accelerated the reaction, and at the end of the reaction, it has gained its original form. So in this, if you see sodium hydroxide or potassium hydroxide, they are acting as catalysts, whereas the actual reaction is CO2 plus calcium hydroxide gives you calcium carbonate plus water plus heat. The other agents which are used are lithium hydroxide, and lithium hydroxide is actually an endothermic reaction as compared to the others, which are exothermic reactions. And so far as exothermic reactions go, I have mentioned heat production here. Bara-lime is the one that produces the maximum amount of heat. In fact, it went out of favor because of this excessive heat production. Indicators and color change. You must know some of the common indicators. What are the indicators that you are using? Phenolphthalein is the one that we use in ROT. Acidic medium, it is colorless, and in basic medium, it is pink. That is, pink is what we start with, and colorless is what it becomes with use. Now, two problems which you must know is, or three rather, compound A, desiccation, and carbon monoxide production with CO2 absorber. So what is compound A? You all know it is produced because of reaction with sevoflurane, and it is produced more when sevoflurane is used for longer durations at low flows. The FDA approval for sevoflurane is not less than minimum flows with sevoflurane should not be less than 2 liters per minute. But now recent studies have proven that even with much lesser flows, 1 liter per minute also, and some studies with even lesser flows are safe in human. What happens is that compound A in mice, it has been proven to be nephrotoxic because mice have that enzyme which is absent in humans, and therefore it is not nephrotoxic for humans. But you must know what is the FDA recommendation, 2 liters per minute. And now, slowly, it has been revised, and up to 2 Mach hours is considered the safe limit as per the books. But again, in practical use, many people have published even much longer use at much lower flows. Desiccation is a problem desiccation is the thing that causes complications with desflurane. So what happens is that you saw that initially this reaction requires water. Later on, it produces water and heat. So the classic example that is given is that you have come that on Saturday evening when you left the OT, you left some gas flow on. So dry gases have been flowing over your carbon dioxide absorber over the weekend. So when you come back on Monday morning, your absorber is absolutely dry. Then you start using desflurane. What happens is that in this dry atmosphere, desflurane decomposes and produces carbon monoxide. So that is when you can have theoretically carbon monoxide poisoning. But again, as you see, if we have used the absorber for some time, it produces water, and therefore that desiccation thing is taken care of after some time. But that first case on Monday morning is when you can get this problem of carbon monoxide production. Heat I have already covered, problem with bara-lime. Then the other thing you saw in the circle system is your ventilator. And common in this figure, we will just touch on 3 common designs of ventilators: the ascending bellows, descending bellows, and the piston. The common ventilator that we see on most of our machines is this ascending bellows machine. So the nomenclature basically is how the bellows, the direction in which the bellows fills up. So basically, how the bellows works is that this is classically called as a bag and bottle. So if you imagine the bag that we were using in the anesthesia machine, and you were using external force to compress it. So in this ventilator, what has happened is your fresh gases fill up the bag from inside, and from outside, we have this airtight bellows housing. And what happens is that at whatever rate I have set, at whatever tidal volume I have set, the computer decides and it pushes in driving gas. So this driving gas is oxygen at gas pipeline pressure, that is 40 to 60 psi. So this chamber, this space outside the bellows, it quickly fills up with the driving gas, which leads to the bellows moving down. And that is how your ventilation is achieved. Then as the patient exhales, the bellows fills up once again and it goes up. So we call it ascending bellows. The descending was absolutely the opposite. In this, for the gases to fill up, there was a weight here. So the bellows would fall, the gases would fill up, and then in the next breath, the bellows will move up and provide inspiration. So if we just compare the safety of the two devices, what was happening was that with the descending bellows ventilator, the descending bellows will descend even if there is a leak in the bellows, even if the entire tidal volume is not being delivered to the patient. Whereas in the ascending bellows, what happens is, and this is what you have seen every day, whenever there is a leak, the bellows will just collapse, not allow any kind of ventilation to happen, and it will trigger off the alarms. So this is generally considered the safer mechanism. In the older machines, especially in older dragger machines, we have used descending bellows ventilators. But these days, mostly you will find ascending bellows, or in the newer dragger machines, you will also find a third type, which is the piston-driven ventilator, where you don't require any driving gas at all. It is a totally mechanical piston-driven device, and that is connected to your computer and which decides the tidal volume rate and other parameters which as per your settings. So these are the three basic ventilator designs. Okay, so once you have understood these concepts about the high pressure, intermediate pressure, and low pressure system, this is good for theory. But what do we do every morning? Every morning we have to go to the OT, check our machine, and then start the case. So checking the machine. Now, if you look at the ASA uh, steps for checking the pre-procedure anesthesia machine checkout, you see there are 15 steps, and these 15 steps can sometimes be quite overwhelming for the young anesthesia resident. So how I have done it in the last many years is that I've just made a mental mnemonic, and that is how I check this machine every morning. And I will just share it with you. It might be of help to you also. So in our OTs, we don't have these scavenging systems. So the first thing that I see the machine and say is no to point number no, because this is the point that deals with checking the scavenging system. So once this 0.9 is out, I am left with 14 points. I have divided them into pairs of 2 each. So 7 pairs, which means now rather than remembering 14 points, I have to remember only 7 points. So the first 2 points is before I have even touched the machine. So the first point is auxiliary oxygen. And this auxiliary oxygen is not the cylinder which is behind your machine. This auxiliary oxygen is another oxygen cylinder with its own valve, with its own breathing circuit, which can be used in case your machine totally fails. So that is the auxiliary oxygen, which should be available with a mechanism for ventilation with a self-inflating bag so that this oxygen can be provided to the patient in case everything else fails. So oxygen auxiliary plus EMBU, we can say, is your first step. Second step is suction. So these are the two steps which we have done even before I have touched the machine. Then as I touch the machine, the first intuitive step is you turn the machine on, see whether all the electricals are working or not. And as I've turned the machine on, what also attracts my attention is that the monitors come on. So at the same time, I check all the monitors, whether all the settings are as per the patient that I'm going to take, all the alarms are working or not. There is no additional alarm, but none of the critical alarms is muted. So after this, we come to checking the high pressure, intermediate pressure, and low pressure system. So high pressure, now I will check the oxygen cylinder, which is behind my machine. The pressure in a full cylinder is 150 bars. So for the emergency, I will have at least 100 bar pressure so that at least it should last me for a few minutes in case the medical gas pipeline goes off. And in case I don't have a medical gas pipeline, then I'll make sure that 2 full cylinders are attached to the machine and I have a sufficient stock of full cylinders to change whenever the oxygen runs low. After the oxygen cylinder, high pressure, I come to the intermediate pressure. So what is the intermediate pressure? Is your medical gas pipeline system. Pressure should be 40 to 60 psi. And I will also do the tug test and see that all the connections are secure. There are no loose connections from the wall. And this will hold steady when I start my case. Next, I come to the vaporizers. So I see that there is adequate amount of agent in each of the vaporizers, and I should also see that I am not able to turn on two vaporizers simultaneously. That is your selector tech mechanism. So sometimes what happens is that if the vaporizer has moved slightly or if it has been changed recently, then it might not be aligned properly, which will allow you to turn on two vaporizers simultaneously, which can be quite harmful. So this is one check that I would like to do at this stage. So once I have checked the vaporizers, then I see whether the flow control knobs are able to deliver the gases fully. And I also check for the negative pressure leak test. Now, a word about the negative pressure leak test. What we see here is that in the modern machines, you have this check valve, which is downstream of the vaporizer. So basically, the purpose of this check valve is that it prevents back pressure from damaging the sensitive equipment. But it also means that if I am using positive pressure to check for a leak, then that positive pressure will be able to check only up till this stage, because beyond that, the positive pressure is not transmitted. So what is the only method left to me to check the system is that I create a negative pressure here and I see if this balloon remains collapsed for 10 seconds, I assume that there is no leak. If that balloon reinflates, then I can suspect that there is a leak somewhere upstream, because that is from where the air has entered and it has led to the balloon re-expanding. So this is the funda behind negative pressure leak test. Now coming back to our tests once again. So now that we have tested everything on the machine, now we move to the scavenging system. Point no, we will not do. We now come to the next two steps. How I remember it is oxygen and carbon dioxide. So we do the oxygen sensor and we see that the carbon dioxide absorber is not exhausted. The color, as I showed you, then there should be no channels, there should be no, and it should not be dry. Then once we have done this, now we come to the step 12, which is your positive pressure leak test. This is now you pressurize your system and see whether there is any leak, so that you have to sustain a pressure of 30 centimeter water for 10 seconds. And if you have done that, then you are sure that there is no leak. These days, you are not doing these tests also because most of these tests are automated. So all these tests which regarding the circuit, which I have just told you, the pressurizing, the negative pressure, these are already done by the machine. But what you will have to do is all these other tests which the machine is not doing. So suppose you have a GE station. So you know that these are the tests that the machine has already done. But obviously the machine has not checked whether the vaporizer is full or not, whether your CO2 absorber is exhausted or not. So those tests you will have to do. What is the pressure in the auxiliary cylinder? What is the pressure in the cylinder? That pressure in the cylinder on the machine, of course, the machine will tell you, but auxiliary cylinder, suction not working. These are things which you have to do and you have to go and do yourself. So once now we have done the positive pressure test, then you come and check the unidirectional valves. So these two is the next pair, that is your positive. So after oxygen and carbon dioxide, the next pair is your positive pressure test and your unidirectional valves. So your positive, your exhalation valve and your inspiratory valve, you see that both of them are functioning properly. When you press the bag, the inspiratory valve moves up, and then when you release the pressure on the bag, the expiratory valve should show motion. And finally, you do the documentation and you come to ventilator settings for the current patient. So this is how we test the machine and we declare that I am ready. Now, this is the list. Now, one more thing which is given in there are two things which you should remember apart from just remembering these 15 tests. So what is that? One is that there are some tests which are to be done once at the beginning of the day, and some tests which have to be done before every case. So it is again logical But just to remember, what I have remembered is 2, 4, 7 and 11 to 15. These are the tests that you have to do before every case. And others, the remaining 7 tests, these are the tests that should have been done once at the beginning of the day's cases. And then another important thing is that you see there are 2 tests here which mandatorily you only have to do. The other tests, some tests are provider and technician, some tests are provider or technician. So there are 2 tests which have to be done by the anesthetist only. One is whether your vaporizers are correctly filled or not, and second is confirm the ventilator settings and evaluate readiness to deliver anesthesia. And that is what we say the anesthesia timeout. And during the anesthesia timeout, Miller recommends this MS MAIDS checklist. You will have your own checklist. Soap me, I have heard many of you use. So whichever whichever checklist you use in your OT, do it. But the anesthesia timeout must be done by the anesthesia provider and not by the technician. So these are the few things that I wanted to share with you. What you must remember is what are the pressures in the high pressure, intermediate pressure, and low pressure system. What are the various components of the anesthesia machine corresponding to each pressure system? And finally, how it works and how it is to be tested before each case, before the beginning of the day's cases. So these are some things which you must remember from today's class. Now, I think we have time for a short quiz question. Identify this device and what is the principle, how it used to work. So for those of you who are interested in quizzing, this is the Ritchie's whistle. So what you can see here is that during normal fresh gas flows, the spindle, this is a spring activated spindle. So the spindle is pushed to the right and there is no oxygen flow. As oxygen pressure falls, this spindle moves to the left because now oxygen pressure is not able to counter the pressure of the spring, which results in the spindle moving to the left, which provides a channel for oxygen to flow through the oxygen port, and this results in a whistling sound which should be audible for more than 60 at more than 60 decibel for more than 7 seconds. And this used to be a oxygen hypoxia prevention device in the older machines, which is now replaced by the low oxygen alarm in our machines. With this, I have finished. If you have any questions, I'd be glad to take them. Thank you very much.
Do we have any questions in the chat box?
I could not see any, Dr. Akhil.
All right. So over to Avnish sir for the closing remarks.
Thank you, Dr. Akhil. I must congratulate Dr. Aditya Sapre for a very nicely explained and a lucid illustration of some of the very basic things which many of the students might have understood for the first time today only, because the way he removed the tray and uncovered all the parts, it really made to understand the functioning of basic anesthesia workstation simple to them. And these are the questions which are invariably asked: how the modern pressure gauge is working, what are the various parts and pressure systems, how the flow is moving, and what are the hazards of having a crack in the tubes, and so many other concepts which he has very elaborately explained. And I think it must be hugely beneficial to the exam going students. And I think it almost covered most of the anesthesia workstation. relatively simple and mechanical ones. While it will be great for the exam goers, they need to brush up these things again and be very clear about what all safety mechanisms are provided in their workstation and do the check and everything religiously, even in their practice. Because this is the most important thing for us. What is an aircraft for a pilot? It is the anesthesia workstation for us. And now it is clear that we have moved even in our day-to-day practice from relatively simple workstations to futuristic workstations, which are more intelligent, AI-driven care systems that automate gas delivery and optimize fresh gas flow and feature high-definition bezel-less touch screens and all. We are using different machines, like I was talking to Tarun. We are using G-Care Station and Dredger. And now the recently introduced, we had a demonstration, Mindrevato X, EX35 and other machines. They provide very good features and elevate the clinical safety to high levels. Automated and smart controls are there. AI-driven algorithm automatically adjust the flow, and it helps reducing the carbon footprints and depletion of ozone layer. And they provide advanced ventilatory modes, which may be universal for all ages, and even lung protective ventilation is there. They're more ergonomic and predictive analytics are provided. So all these things are there. But for a student, it is the basic things, how the machine functions, what are the different parts, what is the physics behind it. So that has been really covered very well, and I congratulate and thank Dr. Aditya Sapre for his presentation and nice explanation for the benefit of exam going students. I take this opportunity to thank JSA to provide this forum and inviting me and giving this opportunity. And it is a pleasure to be with the old friends, Dr. Tarun Lal and Dr. Chitra.
Thank you, sir. Thank you. It's just great to have you with us. We should
Thanks,
connect
Dr.
again, sir. Another platform. Yeah, that's true. So that's true. Very good. We should have more of these. We should have more of these, sir. That is great. I remember
Thanks,
you
Dr.
so well,
Arun.
Dr. Anish, sir. I remember you so well. It's just been so many years, so many years.
Yeah. Thanks,
Amazing.
Dr. Arun, Dr. Akhil,
Yeah.
and Clarinet people, and Trishna for coordinating everything so nicely. So if there is nothing else, I think that's all from my end.
Thank
From
you,
my
sir.
side, sir, just sorry to interrupt, ma'am. From my side also, sir, thank you. Thanks to Dr. Akhil for giving me this chance and for this interaction with all of you. And thank you, sir, for the kind words. Thank you very much.
Thank you, sir.
Thank you. Yeah.
Thank you to all the speakers and attendees for making this a very insightful and engaging session. And it was truly a pleasure for Clarinet to host such a meaningful event. And we deeply appreciate the opportunity and look forward to welcoming you again on our platform in the near future. So with this, we are closing the meeting here. Thank you so much once again. Thank you, everyone.
Thank you, sir. Thank you.